So in this video, I would like to go through certain parts of the details in terms of constraints and loads, as I have promised to do for this week. Of course, I'm going to do it for ABAQUS. If someone is still using Patra and Nastran, then we will do it for you in the classroom. Or if you are an online student, please send us an email so that we can record that as well as soon as possible and put it up. Now, I opened a standard student edition 614, as you can see here. And I can close this off to start the session. I'm not going to build any model particularly here, so I'm going to just look at some of the details. So if you remember from the first couple of practicals that we did through the videos or the one that we did in the class, there was a time when we set up the step after we had made the assembly so that we can define the loads on it. And only after setting up the steps, we were able to define some loads and boundary conditions that could be applied to the model. Now today I want to go through this list of loads and boundary conditions because it's extremely important for us to know what kind of constraints are available to us. Now in structures, in structural modeling or structural analysis, there are certain limited number of loads that we are always going to use. They're going to be displacement loads. So of course you can apply a load in the form of a displacement. So if you want to displace something by 2 millimeters while the other end is fixed, that's a displacement load. You can also apply a displacement constraint. That means you don't want a part of the body or something not to move. So you apply a displacement boundary condition. You can apply a concentrated load. So if you are pulling something with a concentrated load just at one single point, or you could apply a distributed load at an edge of an object or at the surface of an object. And these distributed loads are all of different kinds. So they have nuances in terms of the software that you're going to use. So let's just look through first the boundary conditions. So boundary conditions are quite simple. Of course, to apply any kind of boundary conditions, we have to have a model that is running. So I'm just going to do any model that I've been working on before. So it's nothing really to do with the course. But let's just open one model so I can flip open this boundary condition. Now here you see that I'd already shown you that when you are in initial condition or in the load condition, you see different kinds of boundary conditions. So in terms of boundary conditions, also called as constraints, you can have symmetry, anti-symmetry, and caster, displacement. That means you want to fix certain things in a certain location. And this is the one you've already seen today, symmetry, anti-symmetry. We didn't do anti-symmetry, but it's actually opposite, so it would be easy for you to see later. So we just pick a point, a line here, and I want you to pay more attention to here, this. So if you say that your entry here, this particular line is symmetric with X, then it automatically proposes certain boundary conditions. And if it is symmetric in Y, then it proposes certain boundary conditions. Same way, if it's Z symmetric, anti-symmetric, it has certain propositions for certain conditions, right? So these are the things that you can apply directly. But of course, I would like you first, when you set up a problem, as I said, when you predict what's going to happen, as a first step, always make sure you know what kind of boundary conditions you want to apply. So don't just blindly apply it. Check these and see if they actually make sense, okay? So these are boundary conditions for initial load. So, well, I don't want to apply it, so I have to cancel. And if I go to load step where I can apply all the loads, it's exactly the same but a few less, okay? The others are not very relevant to you because we are not going to use initial conditions, but they are available to apply for initial velocity. For example, if you have an impactor falling on a certain body, then you can apply the falling of the body as an initial velocity. So that means it is moving at a certain rate before you start the analysis. Now let's open the loads. Now for loads, of course, we also know that under initial we cannot apply any load, so it always has to be in the step that you create for acting of the load on the structure. And within this step, you will see different kinds of loads here. There are quite many. Not all of them can be applied to your model, but they are available to you for different kinds of structures or different kinds of analysis that you will be doing. So of course, the usual ones that you will use are concentrated force, you have moments, you can apply pressure loads. That means if you have an enclosed space or you have a surface where you would like to apply distributed load over the entire area, so Newton per square millimeter, then you can also apply a pressure. If you have a shell that you have created and you want to apply an edge load to it, like a distributed load, but only at its edge, pointing inwards, outwards, then you can also use the shell edge load. Similarly, the surface traction is also a distributed load. So I told you before that when you apply a distributed load, depending on the software you're using, it could have different terms. So you also have the body force, the line load, which also act as distributed loads at a certain different level or certain different element type. So before you start applying more complicated loads in the future, which we will not be using, unfortunately, in the course because of lack of time, when you do it for your master thesis or for other projects and you want to find out whether the load can be applied to your particular case and if it's suitable, I would recommend you, as usual, to go to the ABAQUS manual, first read up what they're asking you, and then make a decision. Now, the load selection is of course something, but you can also choose how you want to apply these loads. Loads can be applied in two ways. Either you can apply it to a geometry, so such as this. If I pick this surface here and I want to apply the load, then I just have this surface as my geometry. What I could also have is a mesh already defined on this geometry and apply the load on the mesh. So the load is already associated directly to the nodes instead of the geometry. Now, the disadvantage of having loads applied to nodes directly is that if I want to change the mesh later on, then I have to also reapply all the loads. So it's always better to associate the load with the geometry and the mesh to the geometry. So then the both are related at some point through the geometry to each other. Now, there is a distinct difference between a concentrated load that is applied and a distributed load that is applied. So if you look at one of these edges, if we pick this edge here, this one, and I say I would like to apply a distributed load, and I say, okay, I pick a shell edge load or a surface traction or whichever one, I would rather go with the shell edge load in this case, and I will apply a certain shell edge load here and pointing outwards, then what the system will do is that it will divide this load equally among all the nodes except the two edge nodes. So the two edge nodes will have half the load each, and the rest will be distributed in between nodes. So the profile that the load will form is not just going to be equal like the straight line where all the load is equal throughout, but it will sort of be like a parabola, so that the load is distributed properly through the entire surface. Yeah, and we don't get unnecessary deformations and distortions at the two corner nodes. If you want, there is an example on the YouTube channel which shows the difference on what happens when you apply loads distinctively to nodes by distributing them equally throughout, or by doing this little manipulation of changing the load that is applied at the two edges. You can follow that and probably give you a little bit more idea of what I was trying to put across to you. But in general, as you see, there are a lot of loads and boundary conditions available. Now, there's another third kind of thing that is quite important, is the constraints here. Now, these constraints are also sort of boundary conditions, but not really boundary conditions. They are constraints to decide or to derive certain relations between or interactions between different parts in the model. This is something we will use in the end of the course, and that's the tie constraint. As the name suggests, you want to tie things together. So if I consider that this is one part and this is another part in this model, so there's a certain line here, so there are two parts in the model, and there are two different parts, there are two separate sketches that I assembled together, two different parts that were put in assembly as instances, as you know, and they have different meshes. So the meshes are not the same at the edge, so the nodes cannot be actually joined together. So you know that when we did the example with the trusses, then we said all the nodes are actually joining each other, right? There are common nodes between the different parts to create continuity. So in this case, if the nodes are not the same, then there is no continuity, and to define or enforce that continuity, we use an extra constraint called the tie constraint. And what the tie constraint does in principle is that it tries to find the closest relational nodes to one node on one body to the other, and tries to form a relation with them such that they sort of move together. Yeah, it sounds a bit more complicated. I'll give you some equations at the end in the last, I think in the second last week, when we will do an example with multiple parts involved, and that will give you a better idea of how the tie constraint works. But basically, if you want to put two objects together and you don't want to mesh them exactly the same, because that's quite tedious and a difficult task, as we will learn next week, then we will be able to use these constraints as the tie constraint. There are other constraints as well, like you can also propose a certain object to be a rigid body. For example, as I gave you example of the impactor. So in an impact situation, if an impactor is hitting a softer target, then the impactor can behave as a rigid body. So I don't need to define any properties about it. It's like really high stiffness. That's a rigid body. You can also couple parts together, so you can do a certain kind of coupling. So you say, okay, if this edge moves 1 millimeter, I want this part to move only half millimeter. Then that's something you can do either with a coupling by defining what kind of coupling it is, opposite, how you can make it, or you can define it by means of an equation. So there are different possibilities of using constraints. This is just a flavor of what I wanted to introduce you to. And slowly you may be using some of these constraints in certain projects. And as far as the course goes, we will only end up using ties, which is the simplest sort of constraint. It's already inbuilt, so it's not much that you have to derive to get it working. Thanks for watching this little get to know your loads, boundary conditions and constraints video. See you next time.